Here. I couldn't see that myself. Okay. People, I propose to do the following. No amount of time dilation jokes will get me away from the fact that I stole some of your time when we did the full circle thing at the end of the lecture. So you're just going to get that amount of time back. So what was it, 20 minutes, 25 minutes or so? 20? This was the moment to say 30 or 45. Yeah, right. Yeah, 2 hours. So instead of stopping them at 6, we'll just stop at 5:30. Is that good for everybody? Yeah. I hope that you saw that it was really important to get the full circle thing going. So because what we now have is that we now know that relativity either comes from Einstein's postulates or these Minkowski postulates. Now, I already had some people come up to me and ask, well, how on earth did Minkowski come up with this? Very good question. And I had somebody asking me, if you didn't know about special relativity already beforehand, why would somebody write down dx squared minus velocity squared dt squared? And the answer is, well, probably nobody would, right? I mean, why would you do that? Now, what of course happened, historically speaking, is that Einstein found his relativity by doing these thought experiments. And then Minkowski later on said, wait a minute, we can summarize this in this particular geometrical way, because we're doing geometry here, if you see what I mean. We talk about distances in space. It just so happens that one contribution to the distance comes with a minus sign. Why? We don't know, but if you do assume it, you will get back everything of Einstein and more, because we got the Lorentz transforms we got back, even though we never had those before. Now, to be fair to Einstein, before he did his Minkowski principle idea of relativity, he also had found the Lorentz transforms. So Einstein already found the Lorentz transforms without knowing about the minus c squared dt squared and such, and he did it by thought experiment. But I hope that you can see that the more elaborate your exercises become, the more elaborate your thought experiments have to be in order to find the right rule. So it's good to have this one framework from which you can derive everything, and that is that thing that we're going to take from now on. You might have noticed we have not used that second postulate at the moment, the principle of relativity, that whatever comes out of your equation should hold for all observers. Now, that's true. We're going to only encounter this at the moment that we're going to do mechanics. So that's going to be week 5 and 6. Okay? So don't worry about that second postulate about, well, everything, the rules of physics should be the same for all observers. That will come later. For now on, we only need one postulate. That's either going to be the Einsteinian speed of light is invariant, or you're going to do the Minkowski thing that this distance, strange distance in space-time has to be the same number. Whatever you do, we've now seen they're completely equivalent. Now, a mathematically puristic person will say, well, you haven't shown the equivalence. You've just shown that if you have one, the Minkowski one, you get back the Einstein one. And to show full equivalence, you also have to do the other way. Okay? If you have done that, then you have really shown that both of these approaches are the same. Now, why do we use the Minkowski one? I already told them a couple of times. One of them is, it does away with thought experiments. So it does away with all the messy stuff that comes from having introduced a particular experiment. And therefore, hopefully also takes away this idea that the experiment, the details of the experiments matter for your results, because they don't. And secondly, because all other relativity, general, all this stuff, all comes from the same idea. Now, how do you go from special relativity to general relativity? It turns out it's the same idea. There is an invariance of a distance. It's just that the distance obeys different rules. Instead of having c squared with a minus sign dt squared plus dx squared dy squared, you have a particular number times dx squared, and a particular other number times dy squared, and a particular other number times dt squared. Now, how to do that is general relativity. Okay, so I think we've done a lot today. We've reformulated all of relativity. We've shown when you're allowed to apply it, inertial systems, and we've shown that one of the things that you will get out is this loss of simultaneity, which probably will solve most of the paradoxes that you might have already encountered yourself. If not, next week. And we're just going to go through all of them and then see everything works out beautifully. Okay? So, what I want to do during the tutorial now is to go through some of the steps that I skipped, the mathematical steps. The most important one is the prove that the Lorentz transforms do indeed leave the Minkowski line element. This is how it's called. The tau, this whole line of things with the dt squared is called the Minkowski line element. What I want to go through with you is prove that it indeed is invariant under the Lorentz transforms. So, show that the tau squared c squared, it's the eigentime times the eigentime squared times the velocity of light squared, that is indeed invariant under Lorentz transforms. Because I wrote down the solution, but I never showed that it's actually true, and it is very important that you see that it is. So I would like to start with this. Shall we do the same as last week? That I just give you some time to work on this? See if you can work this out. Then ask somebody if he or she can present it. See if they've actually figured it out. Yeah. Yeah. Right. Joyce, do you have any idea what we're talking about? No. Okay. Oh, that goes for both of you, of course. Yeah. Oh, everybody knows this, of course. No, it's fine. But let me just write down the exercise in more mathematical detail. Okay. So we have this thing. We call this the Minkowski line element. It's c squared times the eigentime squared, and I say that it's equal to this. Very brief summary of the second half of the lecture of just now. Then I made another statement, and I said, but this is always equal to, well, the same expression, but note that I write primes everywhere now. By which I mean that if you go to another reference system, where you don't measure x's, but you measure x primes, and where you don't measure y's, but you measure y primes, you don't measure z's, but z primes, you don't measure t, but t primes, you know that these numbers will change because of Lorentz contraction and time dilation.
Are the primes the derivative of?
No, it just means some other person's time, or some other person's distance.
And x, y, and z, is it the like the x-axis one?
Yes.
The point, the coordinates?
Yes. And here is where the physics lies. The fact that this is the same, this particular combination is the same, even though the dt's are not the same, left side and right side. The dx is not the same, the y is not the same, the dz is not the same, but this combination is the same. This is not the question yet, this is just a summary of the second half of the lecture. Then I claimed that this particular way of going from one person's coordinates to the other person's coordinates, it's called the Lorentz transforms, obeys this rule with the exclamation mark.
What does that mean?
That well, I can see that question twofold. One of them is, do you mean me? Is your question, what do these things mean?
Are those just the t? It's basically what we did last time. T equal to gamma t0.
Yes, plus extra. Yes.
Plus extra.
Okay.
What is that plus extra?
Okay. The plus extra is when, if you remember, last week we had the situation where if you wanted to calculate somebody's dt, if you knew your dt,
Yeah.
one of the dt's had to be in a frame where the two events happened at the same location.
The same location.
If they don't happen at the same location, there's a dx in between those two. Then you get a bigger equation. That's this one. So here's a more general version of the one that we saw last week. Same with Lorentz contraction. That's this one plus extra. And my claim is prove that these two obey this law. It's a question of mathematics, not in physics. Who has it solved? 1, 2, 1. Okay. want to give it a couple of minutes more? Just give it a couple of more minutes and then see if you can work it out.
But can I ask? Sure. Like if it's correct. It's enough if I plugged in the prime ones and I got the normal ones, so it means I've got two systems. That's
exactly the opposite. If you had plugged in the primed ones, you get back the same thing that you would have gotten if you had the non-primed ones, then you have shown that it's apparently the same.
Okay.
Okay, so that's another person who solved it. Good. Or two, I think. So important. Without the Lorentz transform, everything that I told you is wrong. You don't want this.
So if we use this, then one will go hypothetical terms. What have we measured if he had been in the same position?
I propose to see if we can solve this together. There were a number of people who found the correct solution. Is there a volunteer? Don't be shy. It's only 30 of your best friends. No volunteers? How about an involuntary volunteer? Come on, guys, I have to give a lecture at Barney Aperture tonight. I'm going to do so much speaking today, so yes, please. Yeah, thank you. I have to save my voice for now. Yes, if you can, yes. And if you haven't seen how this works, I have seen her result just a second ago. Hers is correct. So I very much assume that what is going to be written on the board now is going to be the right answer. So we'll see. And if not, somebody will protest. And that somebody could be me. So, so everybody, just don't passively wait and hope that she writes down the correct thing. See if you follow her steps, yes? There might be a mistake there, and you might be the person who's going to figure it out. Where do I start?
So I took the situation that we had in the lecture, where there, this is 0 because it's in a plane. Yeah. Okay. And so then I plug in the dt from the St. Lorentz. And I plug in the dx prime as well. And here dt is the same as d tau, so those are like the prime and the normal ones are two different reference frames. And what I'm going to prove is that this will be the same for the prime and for the not prime ones. And I just plug in those two.
Do you see the strategy before she does the algebra? While you keep on writing, for people who maybe haven't immediately seen what she's going to do, it's correct what she's doing. What she's going to do is she's going to say, well, if this particular expression is an invariant, that means I should get the same result out regardless whether I put in the primes or the unprimes, right? This combination has to be the same for both. So what she's going to do, she's going to take the primed version, replace all the primed versions by the non-primed versions using the Lorentz transforms. If it works out, she should get back the exact expression without the primes. Because then apparently what she had shown is that it didn't matter if you put in the primes or the non-primes, you get the same answer anyway. And that's exactly what we mean by the word invariant. So she took the expression, she's going to put the primed version in, replace it by the non-primed version, and show that the end result is what you would have gotten if you never started with the primes in the first place.
So I put the gamma squared in here on the side so it doesn't bother me. And then here this goes away, and because of the minus sign here, this will be basically the same thing as this thing. So I can just cross both out. And then I get
in this, why do you assume y and z are 0?
No, you have to ask Marina.
Well, I took the example from the lecture where we had them as zeros, because otherwise it would be too big.
There will be lots of writing, but I will say something about this in a second after she's done.
Ah.
So you can only assume there's 0 if it's on a plane, right?
Yes.
Yeah.
So
And then the question is,
what happens
c
if it's
squared, so you have c squared over c squared dx, and d to the power 4 to c.
plane.
Yeah, because there's c outside of the brackets.
Oh,
So
sorry.
there was c squared,
Okay,
yeah.
never mind. Thanks.
I will make a comment about this in a second. Yes. You seem to have gotten like the square at the left hand side.
Here?
Yeah, that equation left hand
No.
side.
I've got this question because there was c squared outside of the brackets. This would be to the power
No,
of...
left hand side. Before the equality side. To left,
Yeah?
left, yes. And the gamma should have a square.
Ah, yeah. Yeah, and then the 1 over gamma squared, that one, will be this, which is the same as this, so this will cross out this bit, and so you'll have... We will have this, which is the same as this part, but without the primes.
Okay, good. Thank you. It's beautifully written there, but let me make a couple of comments. Thank you, thank you. This is correct, yes? So again, the logic that she has applied was that she said, well, let's start with what we said should be an invariant. That's this expression. And then she said, well, I'm going to write it in terms of primed. But the claim that it is invariant is the same thing as saying, well, it should give you the same number even if I had not put the primed versions in, the unprimed versions. Yes, exactly this is the invariant, that this expression is the same as you would have gotten without the primes. So what she's going to do is she's going to take the primed version, work through it, and then find that indeed it's given by this. And therefore it is invariant. That's what she's doing. Now, how does she do that? She says, well, dt primed is given by the Lorentz transform. Plus or minus sign doesn't matter. Well, it matters for your exercise, but not for the invariance. So she's replaced dt primed by this expression. She's also replaced dx prime by this expression, and then she just went through the algebra. From this moment on downward, there's no physics. This is just you doing the squares. And if you do that correctly, and she has, you will find that you have a square here, so that means it gives you dt squared, that's this one. It gives you dx squared, and then a v squared, and c to the fourth somewhere, that's here-ish, I think. But you also get this. That gives you 2 times this times that with a plus or minus sign. But if you do the same squaring here, you will also find a dx and a dt with a plus minus, but now with an overall minus. So whatever you had chosen, right, you get here the plus minus. Here you get a plus minus because of the square, but this minus will make it minus plus. So this will always cancel that, regardless whether you had a plus or a minus. They always drop out. And finally what she did was, okay, the only thing that I have left are terms that say something about dt squared and dx squared, and she grouped everything together. Everything that goes with dt squared she put together, everything goes with dx squared she put together. That's ultimately what she did here. Here's everything that went with dt squared. Here's everything that went with dx squared. And then she made the final step that apparently the algebra tells you it has to be multiplied by 1 minus v squared over c squared, which cancels exactly the 1 over gamma on the other side. Long story short, she ends up here, which you will recognize is exactly that expression. Exactly what she set out to prove. So this was the strategy. She's now proven that indeed these two make sure that this will come out the same as that. That she has now proven. A couple of comments. One of them was she did away with the dy and the dz. Now, I did so too in the lecture. And I said I don't want to keep on writing dy squared and dz squared. There's a deeper reason here. And that is that we are now looking at things that are moving in a certain straight line. Agreed? Now, if I have an xy system here, and something happens to be moving in that direction, I just rotate my axis such that it lies along the x-axis. Agreed? You don't have to. I mean, you're free to keep it in this system, but your life is going to be mathematically more cumbersome. Same physics, just the writing out is going to be more difficult. So what she implicitly did, and I did too actually during my lecture, by setting this and this to 0, I secretly rotated my coordinate frame such that the direction was always along the x direction. And I don't have to worry about the y's and the z's. Now, because I did that, that comes with a very important note, and that is that these equations only hold at the moment that the two observers are moving with respect to each other in x direction. This v, the velocity with which the two observers are moving with respect to each other, should be in x direction, otherwise these do not hold. If you find that you have a situation where things are not moving in x direction with respect to each other, rotate your coordinate system such that they do, and then you can still apply it. That was that. Any questions? If not, that's good news, because that means that you have now seen that this really does keep the Minkowski line element invariant, and therefore everything that we did was correct. Now here's the second exercise. So we now know that this is true. One of the things that we proved using these Lorentz transforms was and because we have at least 2 people in the audience who were not here during the lecture, is somebody willing to explain what it says here? We derived this, it's very important. Can somebody give a short summary? This equation tells you something, what does it say? For the people who were not there during the lecture.
So if you have if you have something moving with a speed v, and you have 2 observers that are traveling along with it, one with a speed of u, or a velocity of u, and the other with a velocity of w, then this will tell you the Oh no, speed v is the relative velocity to each other.
Yes.
And then this will tell you, knowing in this case u and v, what the w is.
Yes.
So the speed of one of the two observers.
Okay, that's entirely correct. So let me rephrase. It's important to have everything really understood. You have one coordinate frame. So that's the x coordinate frame. And in that coordinate frame you see something flying with a speed u. So if you would measure how fast this is flying, you measure how many meters it travels as seen by you. Let's give you dx. You divide by how many seconds that took, that's dt, that gives you a velocity, that's u. This is the velocity that you would measure in this frame. Now, we have a second frame. The second frame is also moving, is also looking at this thing. And the question now is, how fast is this thing going with respect to this coordinate frame, the x prime coordinate frame? I call that velocity w. The relative velocity between x and x prime coordinate frame, that I call v. Now, what we derived during the lecture was, if you know that the guy in the blue coordinate system sees a thing fly with u, how fast does the guy in the red coordinate system see the thing fly? Non-relativistic physics would tell you, oh, that's just u minus v. But we went through a calculation using the Lorentz transforms that we now are sure are true. And we found that it's not u minus v, it's u minus v divided by something else. Okay, this is what we did during the lecture. This is what these symbols mean. Okay, short summary. I have two questions. And I want to do the same kind of style here, see if you can work this out for yourself. Exercise A is, suppose that what this tells you is, if you know what u is, what is w going to be? What is the opposite question? Suppose that I give you w, I know how fast the thing is moving with respect to the red frame, and I want to know how fast it's moving with respect to the blue frame. So I want to know u and some function in which there is a w. What is that function? There will be a B exercise in a moment. You already see it, I think, or?
I think, I thought it'd be the same, just you replace W and U. So it would be W minus V over 1 over W.
I hear the answer. I'm not saying yes or no. I just would like to see what other people make of this. The question is clear, yes? We have now, you can now calculate using this what W is if you know what U is. I want the opposite. Suppose that you know what W is, what is U?
I kind of agree with that, because how do you, I mean, a reference frame could be anything. It depends on what you make U and what you make W.
The sign will change, though.
I heard two different things now. Let's go with her question first. And I think if I understand the logic behind this, well, you're free to choose whatever frame anyway. You might as well just, you would have the same equation, but with all w's replaced by v's, by something like this?
Yes.
Okay.
I think so.
And I think I understand the logic here. The logic would be something like, oh, but wait a minute. You're free to choose whatever frame anyway.
I
So
suppose your question is if you're given.
yes.
Okay.
What you're now doing is you're just redefining labels. You're saying, oh, I'm just going to call this U from now, and I'm going to call this W. No. Given that these names are given.
Yeah.
Okay? So at the moment, this is not correct. Now, for the people who are already see the answer, let me already write down what your exercise B is, so everybody has something to work on. What we saw during the lecture was, if U is C, then automatically V must also be C, regardless of what V was. Here's a question. Suppose that some person, the guy in the blue frame, sees this thing fly around with a velocity that is bigger than C. Then you say, but no, nothing can go faster than the speed of light. We haven't proven it yet. We only have our postulate by Minkowski. This we have proven now. We have not yet proven what happens if you can go faster than the speed of light, yes or no. So suppose, for funsies' sake, that you see something fly around with a velocity higher than C. Can you find out what happens to W? Is it also bigger than C? Is it smaller than C? Is it C? So the question is it smaller than C, bigger than C, or is it C? It's a mathematical exercise, but maybe there you can already see some physics in there. And if you want, you can do the same exercise in a different way, and that is that, well, suppose that somebody sees something fly with smaller than C. Then what happens to W? Does the other guy see it go smaller than C, bigger than C, or equal to C? So it's 3 exercises, but the last 2 are very similar. So let's see if you can find this out, and then I'll attach some physics to it after we found the answer.
Could you explain the second question again?
Yes. Suppose that you are in a blue frame and you see something fly around, and this velocity with which that thing is flying around with respect to you is bigger than C.
Okay.
Okay. The question is, does then the guy in the other coordinate system also see that thing fly around with bigger than C or smaller? Maybe there's a mathematical way of answering, and maybe there's a physical way. The answer is both, but let's see if, how you get there.
Which one's the one that sees the bigger than C? Is it the one stationary or the one moving?
Wait a minute. What do you mean by stationary? So can you rephrase the question?
Isn't there's one person that's seeing the ball traveling,
Yes.
and that ball is traveling and covering a larger distance, right? I mean,
Yes.
there's another one who's kind of going at a speed, but not quite as much as the speed. of the
I
ball.
never specified how fast he was going with respect to the ball. So what you're asking now is, what is V?
Yeah.
And saying unspecified. We saw during the lecture that this thing, if one sees will go with C, then the other one does as well, was irrespective of V.
Yeah, but one of them is still moving. One of the two.
It depends on what reference frame you're in. But you're asking. It sounds as if you're asking. Well, who's the guy standing still? The whole standing still question is out of the window. There's relativity. That means you cannot say who is a person who's standing still. What reference frame is standing still? The only thing you can say is that they're moving with respect to each other, and that's the only number that you're given. That's V.
And the ball with respect to
Yes. But you cannot say, well, it's the ball that's really standing still, or it's the U that's really standing still, or it's the other guy standing still. Yes?
Can we still assume that the V is smaller than C? Or
Oh, that is a good question. Does it matter?
And V is positive?
it must.
Yeah, it must. Yeah, not necessarily, but let's say for definitiveness, yes, that it is. Does it matter? It's an open question. I don't know.
I think so.
Okay.
You just rewrite this map.
So maybe we have an involuntary volunteer at the moment. No, you don't have to. You don't have to.
That's what is what I was I mean, you just give your order.
How do you get your other system?
Because you multiply everything. And then you
By
just...
double.
No, by this. Multiply everything by this, then put you out of bracket, and then like divide this part by that.
Usually when we do that, just do it.
Shall we give exercise A a shot? I've heard at least 2 different answers. Who wants to take a shot?
Just A?
Just A. Okay, well there you go. Can you write with that one? Stand over here. Okay, let's see how exercise A turns out.
So basically, I just take this, multiply it with that.
So you're going for the algebraic, yes? So
Yeah.
you're just going to go through the math, okay.
I feel like it's easier to convince people when you can actually write it down. And you're like, yeah, what?
Okay.
Okay. So then. I multiply everything by c squared. And then I just put the stuff with u on one side and the stuff without u on the other side. And you get this.
Yes, correct.
And then
That's true.
oops.
Yeah,
Yeah.
see how you just make mistakes on the way.
What was I doing? Oh yeah, I was just doing some. Yeah, and then basically you just have this.
Can I really tell from here? Okay, there you go.
I also found it's possible to make it from like the very beginning, from the graph.
I'm not sure I understand. what
Like how we derived the equation of W.
Oh yeah, sure. Yeah, yeah,
Can make
absolutely.
that as
Yeah,
well.
yeah. Absolutely. So, thank you. Yeah, it's completely correct, but let's go through the steps. There's at least 3 ways I'm not thinking that you can look at this. One of them is the way that Ash did it, is just by just going through the maths. Yes? You want to have this equation, what to solve it for you. And, well, you can multiply both sides by the denominator, blah, 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 etc., etc., etc. You get here. And then you find, very interesting, that it's really just the same expression with the u and the w swapped, and the minus signs have turned into plus signs. Now that is a second way of looking at it, because what does this minus sign tell you? It tells you whether these 2 observers in the red and the blue frame are moving in this direction with respect to each other or the other direction. Do you see that? V is just a matter of is the other person going in this way with regards to me or the other way. Now, if you are in the blue frame and you're looking at the red frame, then the red frame this is the plus direction, is moving in the plus direction. V would come with a plus sign, right? But if you were in the red frame, you would have seen the blue one move away from you in that direction into the negative. So apparently, switching from one frame to the other just results in turning V, your relative velocity, into minus V, just from a completely physics point of view. And that's exactly what you could also have done, is that you said, well, if I want to know how the other person moves with respect to me, I just replace all my V's by minus V's. My U's become W's because we're now looking at the other person's velocity, and then you would have immediately gotten this. So it makes perfect sense. So, so this is completely correct. You could also see this from a physics perspective. There's a more math/physics way of looking at it, and that is that going back to our Lorentz transforms, we got this minus sign from the Lorentz transforms because in our derivation we took here the minus sign. Remember? This is where this minus sign came from. If we had chosen the plus sign here, we would have gotten plus signs here. Now, I told you during the lecture that the difference between the Lorentz transforms with a plus and the minus sign was again whether you are moving this way with respect to each other or that way. So you could have also just said, well, based on the Lorentz transforms, seen from the red frame, the other person is moving away from me with a minus sign and taking the extra minus sign here and made all the minus pluses. So there's 3 ways of getting to the same result. So that's easy enough. Okay, so there we go. In the time that we have, is there somebody who's already taking a shot at this one? Yeah, sure, absolutely. Do you want to do it here? Yeah. Okay, good. While she's making her way up here, this is very important, yes?
I don't know if mine is right.
No, that's fine. We'll just go and see what happens. It's very important because we haven't shown yet that you cannot go faster than this C. We've only shown in our current derivations is if somebody sees something go with C, then the other person does so as well. But suppose that if we go through this calculation, you find that if some person sees it go faster than C, is it then possible for the other person to see it go slower than C? The reason that I'm asking is very important. I'll be there in a second.
Sorry.
No, it's fine, it's fine, it's fine, it's fine. But I want you to understand why this is important. It's not just a nice mathematical exercise. There's importance here, physical importance. Suppose that we are going to find, we're not, but suppose that we would find that if some person sees something go faster than C, then the other person will see it go slower than C. Suppose that is the case. The difference between the one person and the other person, how fast they are moving with respect to each other, right? Their relative velocity V. If somebody sees something go faster than C and the other one does not, then apparently it is possible to move a reference frame in such a way that something that went faster than light does not go faster than light anymore, and back and forth. Do you see that? If we find that one person sees go faster than C and the other one does not, then apparently you can break through the C barrier. If you want to see something go faster than the speed of light, just go to another reference frame in which it goes faster than the speed of light. If you are in a frame where things already go faster than the speed of light, then maybe you can just go to a reference frame, choose your V appropriately, where all of a sudden it goes less than the speed of light. So if we're going to find that U bigger than C, somebody sees it go faster than light, and the other person does not see it go faster than light, then apparently you can just make things go faster or slower than the speed of light by choosing your appropriate reference frame. And that would mean that apparently the speed of light is not the ultimate velocity. You can just switch it to bigger and smaller just by choosing the right V. The fact that we're going to find that it's not, that I'm already giving away the answer, you will find, if you do the exercise correctly, if U is bigger than C, then W is also bigger than C. You will find that. And this exercise is the same thing. If somebody sees it go slower than C, then everybody will see it go slower than C. Exercise B and exercise C are really just one big way of saying that it is impossible to make something go faster or slower than C just by switching coordinate frames. If we find that that is the case, and yes, that is the case, that means apparently the speed of light is a barrier that cannot be broken. That's still not saying that you cannot go with the speed of light. It just says that if there's only one person in the whole universe that sees something go slow with the speed of light, then everybody else will as well. That's the physical importance of this exercise.
Does that tie in with the invariance quality or?
No.
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 Okay.
Because, no, the answer is simple. No.
Yeah.
Sure. Okay, let's see. You make a vector.
Sorry,
No, it's
I've been
fine.
doing multivariable, which is why in my head everything is a vector.
Well, I mean, velocity is a vector, okay? So, but then again, we also said, well, let's always switch to a frame where things only move in x direction, so that makes it a non-vector, but that's fine. I mean, if you want to write vectors, fine. Sure, go ahead. Roll out it as vectors. Can you explain what you are doing? I mean, I think I can follow.
It's just simple substitution. I just substituted the equation we got in A into for U, and then I've been solving it to try and isolate W and get C in terms of W.
That's beautiful.
Yeah.
So,
I mean,
I'm just going to repeat what she said. She said that, well, assume that U is bigger than C. Then replace U by what we now know how it can be written in terms of W, and then find if W is also bigger than C. It's an algebraic inequality, yes? U is bigger than C, so that means this expression in terms of W must be bigger than C, then solve for W. Should it be bigger or smaller than C? That's her program. And it's mathematically sound.
oh, I have a question. Do you write C? Can you write C in terms of a vector, or should it just be C? Should there ever be an arrow in?
It depends. If you're literally looking at a thing that is moving at the speed of light, and you want to give its velocity, then you write C as a vector, because then the thing has a direction.
Okay.
In our Minkowski line element, the role of C is that of a number and not a vector.
Okay. Sorry, I didn't know if I should write it, so I didn't.
And she's already solved it beautifully. Okay, perfect. Thank you. Again, the program, this was perfect, thank you. So the program was very simple. We're going to assume that this is true because that was the starting point of the exercise. We know that U can be written, this was exercise A, as such. Put this stuff in, do the algebra, we now have an inequality in terms of W. Work through the algebra, you'll find W must then also be bigger than C. And there you go. So that means if somebody sees something move with the speed of bigger than the speed of light, then any other person will as well. Notice, and that's very important, and Lizzie, I think this was your question. It doesn't matter what V itself was. Do you see that? So because this, here the C minus V dropped out on both sides, regardless of the value of V. That's very important. So no matter how you're going to choose your V, no matter what other reference system you're going to try to be, it will always drop out. So hypothetically, and let's assume that we don't know that you yourself cannot go faster than C. Let's suppose that you try to make V itself bigger than C. Okay, so that the reference frames go faster than C. That's impossible for reasons that we'll see later, but suppose that it is. Then still it will drop out. So you cannot even make something go slower than the speed of light by going into a new reference frame that itself goes faster than the speed of light. How about going in the other direction? You just move away from the thing that you're looking at. Okay, then V becomes minus V, it will still drop out. Whatever you do, it is impossible to go to a reference frame in which all of a sudden something moves at the speed of light goes slower. Now exercise C is really the same thing, right? Just reverse all the equality signs. inequality size. So that means, and that is the most important thing for today, I think, for the tutorial, if some person, one single person in the universe sees something move lower than the speed of light, then any other person in whatever reference frame will also see it go slower than the speed of light. Even if that reference frame itself goes with the speed of light or bigger or smaller or what have you, it will always drop out. So that means we've now demonstrated a couple of very important things that will be very difficult using just Gedanken experiments. We've now found that the speed of light, whatever it is an impenetrable barrier. You cannot go through it. No matter what you do, what other reference frame you want to go, the speed of light will always be that thing that you cannot make things go faster or slower when you go into the appropriate reference frame. Note, we still haven't proven that you yourself cannot go with the speed of light. That still is an open question. But you see, we're building up everything that we knew, yes? Have you noticed that so far everything came from this? Because this rule came from this. Now, where did this come from? That came from this invariance. I've really only just made one postulate to get all of this out. So when I introduced the C in the lecture where I said, well, some conversion factor has to be there, I never said it was invariant, and never said it was an impenetrable barrier, and never made any specific statement. I also didn't say it was light that moved with that thing, or that there was something in the universe at all that moves with that thing. I just said there has to be a conversion factor, and just from following the maths, you find all these special properties that this particular velocity has. So we're really on very strong mathematical footing here. One postulate, all this physics comes out. It means extremely beautiful. All right. Let's do one last exercise together immediately. And that is, remember that if you have this postulate, you can get time dilation out if you just choose your events properly. We said, well, let's take two exploding firecrackers, make sure that one of the observers sees them at the same location. That means that these all drop out. Do some math, you find time dilation. Then I said, well, see if we can get Lorentz contraction out. You tell me, how do you get it out? It's in there, but how do you get it out? Sure. Oh yeah, absolutely. I showed you during the lecture that under this postulate that already gave us such a treasure trove of information, but I said that this postulate gives you time dilation. I claimed that it also gives you Lorentz contraction. Question, can you show that is the case? Well, this I want to do right here, right now, just together with you guys, unless somebody has an immediate suggestion. The stick comes flying by. Oh, sorry.
Yeah, it's just on the board, it's the same method, like the x prime, the formula on the bottom of those two.
With this one, or?
Yeah, the Lorentz.
Yes.
Yeah, the one on the bottom, if you just fill it in, then you keep it for a while.
So you make dt 0?
Yeah.
And then you get an equation that says, well, one dx is gamma times the other dx, or something like that, yes? But which dx is which? I mean, I'm hearing you do a mathematical operation, but what is the physics? So I want to make it specific. The stick comes flying by, and I want to know what its length is. In order to apply these Lorentz transforms, you have to identify what your two events are. We've seen during the exercises last week that numbers change depending on what your two events are. You must be very careful that you're always talking about the same two events. So what I'm asking you really is sure, I mean I can put in numbers left and right, but I have to first specify what are my events. Otherwise, some new numbers will come out, but I don't know what these things mean. So I have to convert this to a physical exercise where the events mean something, have a physical meaning. So this is my question. The question is not can you put dx is 0 somewhere and see what comes out. The question is what are the two events, so that you really see what happens.
You should be measuring the length at the same time, right?
Yes. Okay.
So you need to be in a reference frame in which you are stationary with respect to the length.
If I want to measure the length of this table, I measure its front end and its back end. But if I'm stationary with respect to the table, I can measure the front end, wait 5 hours, and then measure the back end. Yes. So.
The two event can be the moment the first part of the sticks goes through me, and the moment the end part of the sticks goes through me.
Okay.
That could be the two events.
That sounds actually pretty good. So tell me what. Okay, so you make 2 events now. So I'm standing here. A table comes flying by.
Yeah.
Okay. My first event is the front edge of the table flies by, and a moment later, sometime later, if it's a very long table that takes 5 hours, but at some point the later end of the thing will fly by. Yes.
Yeah.
Okay. Those are my 2 events. So we're going to go with that. Good. Okay. So tell me, what number have we now specified?
You know, the time the time it took for the table to go for the end beginning.
Yes. So we have our 2 events. The front end of the table flies by and the back end of the table flies by. That gives me a certain amount of time. You tell me, am I the primed person or the non-primed person? Doesn't matter for the exercise, we just have to specify.
Let's be the primed person.
Okay, I'm the primed person. So the unprimed person is the guy sitting on the table, okay? And I'm the guy seeing the table fly by.
It would be maybe easier if
It's just labeling, it doesn't matter, so we can just...
so whatever.
Okay, let's stick with your original choice. I'm the primed guy, the guy who sees the table fly by. Front end goes by, 1 event. Back end goes by, 2nd event. Okay, so that means, and this is what you said, I've measured a certain amount of time between these 2 events, and because I'm in the primed frame, I'm going to call this dt primed, yes? Okay, now I was hoping to measure length, so what do I do now? I have a certain amount of time on my watch before the front and the back end flew by. How do I get the length of the table out?
Speed of the speed multiplied by the time it takes.
Okay, so I'm hearing this. It's the length of the table as seen by me, so let's call it L primed, divided by how fast the thing was flying by. Oh, that sounds perfectly reasonable. Something like this. Okay, now what? We're doing fine, by the way. I'm just see if we can... We have some Lorentz transforms, we have a delta t. Things are going fine.
Isn't the velocity the same for circles?
No, the guy who's sitting on the thing will see the table move with 0 velocity.
So we see the events at the same moment.
Who does?
We haven't-
No. You made it. You chose your events such that they explicitly do not happen at the same moment. It's fine though. I mean, we can revert it to length, so we're on the right track here. The question is how to continue.
Maybe you fill in the dt primed.
This one?
Yeah.
Well, let's see what happens. So we're going to take a Lorentz transform. We know that dt primed, for the guy who sees the table fly by, we'll see gamma dt plus or minus what happens d over c squared dx.
dt is 0.
Which one is 0?
dt for the guy on the table.
Is it?
Oh no.
So now you're now the guy on the table. I'm wondering now, what is dt without the prime? What is dx without the prime? The guy on the table.
The x is just the proper length.
It is, but how can you? You're right, but the x is the proper length because look, I'm a guy sitting on a table. You know, let me actually go physically sit on this table here, and this whole table is flying by. And you know, I'm going to take you. Okay, so the front end is now moving past you. That is your first event. That was what we called the first event. I also look at the same event. So my event is going to be when this part of the table flies by you. Okay, I take a time measurement. There we go. The thing flies by. At some point I see this whole table fly by the back end of you. That was our second event. I measure how much time was in between there. That's certainly not 0. Do you agree? Some number. That is dt.
But that was at the same location. So we can say that we have proper time thingy, and then relate to that. So we can say that dt prime is the same as d tau because it happens at the same location. Measuring and then we can plug in what we find in the upper equation. So c squared times L prime over V is equals to
Is it?
yeah. and then we can try to.
That is entirely correct, although what you're now doing is you're just rewriting these things back into these.
Yeah, but I don't know if you can already use those.
You should in principle be able, because this thing we saw today is really just a rewrite of this.
Okay, it's just like, I don't know if the exercise was just using the upper.
It will probably work. It will probably give you the right answer. We're there, but we're not quite there. Do you see that? So the DT, the guy on the table watching the front end and the back end pass you, it will not be 0.
The X divide everything by dt. Like, not divide, but like put it out.
Is that what you meant?
Yeah.
That
But
works.
there would be dx over dt, right? Inside of the
What
brackets.
about the dx?
It turns into another view.
Switch to V, you have
That gave you
V
V
squared.
squared.
I see.
Okay.
Ah.
Wouldn't the X be 0?
No,
Sorry?
dx prime is 0.
The X normal, the DX wouldn't be that 0. Because the two events are happening at the same location, right?
But for the guy on the table, it
Yeah, but we already
we're
put that
measuring
in.
the thing.
Well, that the DX is not free.
The dx primed would be 0 in this particular setup. And we already put that in, because we took this one and we put the x, well, we can put dx prime to 0. Hey! We've only been using this equation, we all still have this one, yeah?
But this one, can we also just, the equation we find down here, it's also the same as 1 over sigma to the square, no?
There's no sigmas.
Gamma to the square, 1 plus minus v squared c squared.
I'm not seeing exactly what part you mean. You might be saying something
I'm
completely
just-
correct and just not seeing it.
If we multiply gamma, and we have the parenthesis downstairs, this, couldn't we rewrite it as 1 over
Sure.
gamma squared?
Why would you write this as 1 over gamma squared?
Because then we only get
Well, not really, because you have a plus minus there.
Oh, there's a, oh, I see. Oh, now I see where this is going. Okay. Well, mind you, there's still an equation that we have not used. This is 0, agreed? So, because for the guy who's seeing the table fly by, the two events, the front end flying by and the back end flying by, happen at the same location. So this second equation will give you that dx equals plus or minus or plus v dt.
No.
Yes. Will that help us?
Well, it just tells you that there is no dilation in space or time for the observer that's on the table.
Yes, I agree with that.
Oh, if we,
No, you can plug in.
maybe if I change back to what I was thinking.
Sure.
In the end we find, so if we consider what is in the parentheses and we say, oh, instead of plus minus, we just choose minus, for example, one of the solutions.
Sure.
We can say that it's the same as 1 over gamma squared.
Yes.
Then we only have 1 over gamma, if we simplify it, over dt is equal to L prime divided by v. Then we just multiply L, v, dt, sorry, by v.
Yeah,
and
I
we
see
get,
what- yes.
and we get dx like L, the normal L.
I see where this is going. What you're saying is, well, choose the minus sign.
Yes.
There's an issue there, though. But let's suppose that we
How
do.
would you explain the plus and then?
Yeah, that's the whole point, of course. I mean, why if the two would you choose that one? But sure, let's do that for a while. And then you say, wait a minute, but this is just 1 over gamma squared.
Yeah.
So this whole thing now together has become 1 over gamma.
Yeah.
Okay. And then your dt is what you say you take from your second Lorentz transform.
No, I take it from the L prime times over v. If I multiply v by dt, I get L, like the L we are supposed to measure.
Oh, yeah.
And then we have L prime is equal to 1 over sigma.
Okay. You're doing, I think, the same thing that I was supposed to, what I was thinking about doing. You were thinking about multiply this with dt.
Yeah.
And so in other words, you take this dt over here, then you have v times dt. That v times dt, according to the second Lorentz transform, will give you just L again.
Yeah.
But now it's going to be, no, it's dx, I'm sorry.
Yeah.
And then you would get L prime over L is 1 over gamma, is what you're saying. Why is this dx, why do we call this L? Because L was the length of the table as seen by the guy sitting on top of it.
Yeah, but what we want is Lorentz contraction, no? Isn't it just like is it like the same as just another way of?
By the way, this is the right solution, but there's more than just the right solution. It is also right derivation. There's a simpler way, by the way, because what we've now done, we've reverted our measurement of how long the thing is by how much time it takes for the thing to fly by. It's correct, but it takes a couple of more steps. We are at the right point, though. Give me a second, okay? Then, just to go through the logic here. So what we did, we said, well, okay, let's take the two events as being this part flies by you and the back end flies by you. The amount of time that it takes, you can convert back to how long you think that the table was, its length. That was this step. Okay? Then we put that into the first Lorentz equation, Lorentz transform, that gave us this, just playing with some maths. Then we, at this moment, somewhat arbitrarily seem to have chosen a minus sign because the whole derivation would not work with the plus sign, so there's a point there. But let's do it for a moment. We're going to use the minus sign here. Then we conclude, oh, wait a minute, this is 1 over gamma squared. Times gamma gives you 1 over gamma. The dt, I'm taking your advice now, I've replaced here, I get a v times dt.
Or
Now,
you can just multiply v times dt.
That's the same, it's a different statement of the same thing. But we're on the same footing here. Then I say, but what is v times dt? Yeah, it's a length. But is that the length of the table? And it is. Because the second Lorentz transform, having taken dx prime to 0, because dx prime is 0, because they happen at the same location for you, gave us that dx is plus or minus v times dt. So taking this dt here, v times dt is, according to the second Lorentz transform, is dx. There's one final subtlety here. It's dx, but is that dx? Is that indeed the same as the length of the table, as seen by the guy on top of the table? Is that true? Why is that true? Because, listen, I'm the guy sitting on the table. Two events. First event is this part flies by you, this part flies by you. I measure in my frame where this happened and where that happened. Is that the length of the table? Yes. What I'm saying here is be very careful what you're saying, oh, dx is probably an L. You have to look at the event, is that indeed your L? In this case it is. And then indeed you will find that how big you see the table is 1 over gamma how big I see the table, which is exactly our Lorentz contraction. Works beautifully.
But why did we choose a minus?
That is a good point. This hinges on us having taken the minus sign. If we had taken the plus sign, it would not have worked, this derivation. Can somebody tell me why it should be the minus sign? Or maybe shouldn't. Maybe it's all wrong.
Don't we factor in the fact that dx is minus plus v dt into the thing? Because we kind of ignore that as well.
Yes. We also ignored the plus minus here. I just call it a plus sign, but that's not much of a point. Because the length of the table, it's 2 meters or it's minus 2 meters depending on where you started measuring. That's that plus minus. It's a different plus minus. Now this minus actually says something, and it had to do with this plus minus. So you tell me, we hope that it's the minus. Why? Why is it the minus? Yes?
Because of the plus that's on top, it's more likely to, the VDT is more likely to be plus in that equation, which means that dx is more likely to be minus if.
Why is it more likely? I don't. It sounds very quantum mechanical to me. But
because we choose it as a plus in the beginning. When we apply the formula,
yes,
we know that dt was equal to 0, but then we could choose either it would be equal to minus vc squared times dx, or it could be plus, but we choose in the L time v that it will be
that is
positive.
Entirely correct.
So then the other one will be negative.
Yes, that is entirely correct. Thank you. It's you gave the right answer. I'm just looking where I can find it on the board. Help me again. What was your answer?
So I said that.
No, he's correct, but I just trouble finding it on the board.
It's just like when we choose to select dt over prime, and we say, okay, we can simplify it by saying that
dt over prime?
Sorry, dt prime, here. And we say, okay, we can simplify it by, well, the thing is when we measure the length, we measure a positive length, we didn't measure the negative length like we could have, like d minus dx squared. So when we write L prime, we choose to write it L prime over V and not minus L prime.
Exactly, that's the whole point. By having chosen the length, right, the length of the table could be 2 meters or minus 2 meters depending on where you start measuring. That implicitly has already chosen for you the plus or minus sign in your Lorentz transform. That's all there is to it.
But we never chose whether it was plus.
Yes, we did, because we said this happens first, and then that happened.
But it can be
and
applied in the minus direction.
You do initial minus one.
Just start with her first. No, because what we're doing, we're taking this amount of time that he would measure, this moment, and then when the next thing flew by, and converted it to a positive length. Do you see that?
We
If
never
I want
said it was positive, like we never discussed it.
Okay, if time flows forward for him, then this thing will fly by first, and then that thing, the back end, yes? If I want to convert that to a plus number, a plus amount of meat for the table, I have to multiply it by plus v, not minus v. Do you see that? The fact that I've taken his plus amount of time between this part flying by and that part fly by, that's a plus number, and I want to convert it to a plus amount of meters, then I have to multiply his dt by a plus v.
So the choice is on the sign of the velocity.
Yes. And because, and we saw before, that the choice of your velocity sign depends on which sign you've chosen here. The fact that I've taken his amount of time between front end and back end flying by as a plus number and converted to a plus amount of distance has implicitly told me that I've taken the plus sign in my v's. And that is fixed the signage in your Lorentz transforms. That's all, sorry. The choice laid in wanting my length to be a plus number. Yes.
It's also another way of saying is also by V. We choose that the object is moving forward, we choose that the object is moving like in the other side.
That could have worked as well, yes. Okay, people, to wrap up. We've seen quite some very important things today. As always, I will write a synopsis of what you have seen, so that means you should always be able to see what point you should have understood by now. I typically try to put this on the same evening that I gave the lecture. Tonight I have to give a talk at Broadening Your Aperture, so it might not be tonight because it usually takes a while, okay? So be home late. So at the very latest will be tomorrow. You will get the recordings, you will get the synopsis, and you will get the exercises from the book that we will work on Friday. So thank you. Sorry?
What's your lecture on?
It's on how you extract gravitational wave data from your noise. It's mathematics, but it's physics.
Do you record that lecture?